the end of the universe might come much sooner than we ever imagined. A recent study that has shaken the astrophysics community worldwide has recalibrated the cosmic clock for when everything goes dark. Shockingly, that moment is arriving far, far earlier than we thought. Closer than you or I could ever picture. Imagine this unbelievable scenario. One day a scientist tells you that this vast, star-filled universe, from endless galaxies to billions of years of cosmic history, even it has an ending. Like a book, with a final page. Like a grand feast, that must one day conclude. And here's the chilling part. This end isn't some unreachable eternity away. It's actually much closer than we've always assumed. A question we once thought was just philosophical speculation has suddenly become a real, numerical countdown. Three scientists from Radboud University in the Netherlands teamed up on a groundbreaking study. Their theory boldly resets the fate of the cosmos, pulling the final countdown much closer to our own timeline by dozens of orders of magnitude. This isn't just a tweak to an equation. It's a deep shock to our entire worldview. Their paper was just published in the respected Journal of Cosmology and Astroparticle Physics. And its core idea stunned the scientific community. They recalculated when the universe will completely decay into heat death, around 10 to the power of 78 years, meaning a 1 followed by 78 zeros. That may sound unimaginably distant, but compared to the old estimate of 10 to the 100 years, a 1 followed by 100 zeros, this means the universe's lifetime has been cut down by staggering orders of magnitude. In fact, it's like dragging the universe's old age several eras closer to us. And this research didn't come out of thin air. It's rooted in a fresh take on Hawking radiation, a classic theory, a daring scientific comeback story. Their proposal doesn't just challenge the entrenched timeline of mainstream cosmology. It shakes our very understanding of how the universe ages and how it all will ultimately end. This reinterpretation of physics is like unlocking a secret door to the universe's destiny. For the first time, we can glimpse the final moment from a whole new perspective. A time when every structure, every particle, even time itself, dissolves into nothingness. In this journey ahead, we'll dive into the most extreme, mysterious objects in the cosmos, white dwarfs, neutron stars, and even black holes once thought to be eternal. Why do they, too, eventually evaporate? Under the pressure of time, we'll uncover how density determines their rate of decay, and reflect on how this discovery could reshape the foundations of modern physics, and ultimately, how it changes our view of the universe's fate. Back in 1975, the legendary physicist Stephen Hawking challenged conventional wisdom with a revolutionary idea. He suggested, black holes aren't just what we thought. Giant cosmic vacuum cleaners, swallowing everything and giving nothing back. Instead, they can actually leak, releasing energy in subtle, yet undeniable ways. Giving something back to the universe? Hawking's bold prediction. Here's a fascinating thought experiment. At the event horizon of a black hole, that invisible boundary where even light can't escape, something remarkable happens. The strange rules of quantum mechanics start to take over. Because a vacuum isn't truly empty. On the tiniest scales, it's constantly flickering with particles and antiparticles. This quantum dance could cause black holes to emit an extremely faint, but very real stream of energy, later known as Hawking radiation. This groundbreaking discovery shattered the old belief that black holes last forever. Hawking radiation means that even the most massive, most powerful black holes will eventually burn out, like a candle slowly fading with time, until they completely evaporate, leaving behind only a faint trace of heat. However, this process is incredibly slow, so slow it rivals the entire age of the universe itself. For a giant black hole, it could take 10 to the power of 60 years to fully release its mass, melting away like an iceberg under the sun. Except this time, we're counting in trillions of years. But Hawking's theory wasn't the end of the story. Decades later, 3 researchers from Radboud University, black hole expert Heino Falk, quantum physicist Michael Wondrich, and mathematical physicist Walter van Zuijl-Lacombe, took the idea a big step further. They proposed that Hawking radiation might not be unique to black holes, but could be a universal effect around any object with an intense gravitational field. In a paper published in early 2023, the team officially introduced the concept of Hawking-like radiation. They pointed out that as long as an object has a sufficiently strong gravitational pull, even without an event horizon like a black hole, it could still slowly leak energy through quantum effects. That means many objects we think of as stable, like neutron stars, white dwarfs, or even certain planets, might already be losing energy at a painfully slow rate. And this was just the beginning of their cosmic exploration. They didn't stop at theory alone. They went a step further, challenging cosmologists to rethink the time scale of the universe itself. If every massive object in existence will one day evaporate through Hawking-like radiation? The question is, how long will it take? In their follow-up work, published in the Journal of Cosmology and Astroparticle Physics and made publicly available through the RCA database, these three researchers took an even bolder step. They not only confirmed that their model could apply across the universe, they also tried to calculate, with actual equations, how long different cosmic objects would last before finally evaporating. This was a groundbreaking, quantitative approach. A countdown from black holes to humanity itself. They confronted a question asked by amateurs and professional scientists alike. If everything eventually fades away, how much time do we really have left? When will the universe's final glow completely go dark? They didn't just ask this question. They pushed further. If every massive body with a strong gravitational field in the cosmos must eventually undergo this Hawking-like energy drain, then, from the purest perspective of physics, how long would it really take before they vanish into the cosmic background radiation? The answer is far closer and lonelier than we imagined. Their conclusion left the entire scientific community stunned. Not just because the results were shocking, but because, in a simple yet precise way, it overturned a timeline we once thought was already settled. The fate of the universe might be much shorter than we ever imagined. For decades, astrophysicists widely believed that white dwarfs remnants of stars like our Sun were cold, fading corpses at the end of their lives, and these relics could linger in the cosmos for 10 to the 100th years. That's a span of time almost indistinguishable from eternity itself. But this new study shows their true lifespans may be nowhere near as long as we thought. In fact, most white dwarfs will completely evaporate after about 10 to the 78th years. Still unimaginably distant. But compared to earlier predictions, it's shorter by dozens of orders of magnitude. Even more surprising, the research further suggests that neutron stars and stellar mass black holes, two wildly different, yet both incredibly dense cosmic objects, actually share almost the same lifespan under the effect of radiation. Roughly 10 to the 67th years. In other words, The time it takes for them to shine, fade, and vanish is almost identical. Even though black holes have far stronger gravity than neutron stars, that result is completely unexpected, almost counterintuitive. After all, black holes are famous for having gravity so powerful that even light can't escape. Naturally, we'd assume they'd last far longer. But in reality, it's precisely that extreme gravity that makes black holes behave differently when it comes to energy flow and in terms of lifespan. They end up neck and neck with neutron stars. The key turning point lies in their very nature. Unlike white dwarfs or neutron stars, black holes don't have a solid, visible surface. Instead, their surface is the event horizon, a fuzzy boundary of no return. This strange structure creates unusual effects. During the radiation process, some particles emitted near the horizon get pulled back by gravity's recoil. This lowers their overall radiation efficiency. By contrast, the radiation from neutron stars and white dwarfs is more direct, more free, which means under the same mechanism, they evaporate faster. This new insight into physics is like dropping a pebble of thought into the endless river of cosmic time, sending ripples outward. It forces us to rethink the long, supposedly endless farewell of the universe. Maybe it's not a slow fade into nothingness, but a much quicker, dramatic collapse, shrinking down into a tighter, more concise finale. This conclusion carries a sense of cosmic destiny. No matter how massive a star is, no matter how dense, nothing can escape this silent unraveling. It's the universe's law of thermal death, not a violent crash, not an explosive spectacle, but a slow, steady evaporation, driven by quantum fluctuations, silent, yet inevitable. The study goes on to explain the real variable that controls radiation rates isn't mass itself, but density. The denser the object, the stronger its gravity, and the harder it is for particles to escape. That slows radiation down. It's like a locked treasure chest. The tighter it's sealed, the harder it is to release what's inside. Density becomes the ultimate measure of how long a star can survive. However, no matter how dense a celestial body is, or how slowly it radiates, given enough time by the universe, even trillions upon trillions of years, eventually, all matter will vanish, dispersing at an imperceptible pace. It's a disappearance that never stops, grinding the entire universe down to nothingness. Building on Hawking's theory of radiation, Fock von Drack, and van Suchlicom launched an extraordinary project, a nearly unprecedented attempt to imagine a universe stripped of collisions, cosmic interactions, and gravitational disturbances, an idealized state of pure simplicity, where only Hawking radiation drives evolution. They calculated which cosmic objects would fade away first in the ultimate endgame. It was almost a purely mathematical meditation, yet it revealed a blueprint for the universe's fate. In their model, there were no galactic interactions, no star mergers, no supernova explosions, not even quantum energy fluctuations. All of that was stripped away. Only one force was left at work: Hawking radiation. Utterly simple, yet infinitely powerful at the quantum level. The last sculptor of the universe's final days. Based on this stripped-down model, their lifespan estimates compressed dramatically, shattering our usual expectations about the longevity of the cosmos. This cold, hard number, in a sense, redefined what the end of the universe even means. No longer a hazy horizon in the distance, but a clear, countable marker of time. According to their calculations, white dwarf stars like our Sun, the dense ashes left after their fuel runs out, will fully evaporate through Hawking radiation in about 10 to the 78th power years. These cooling star remnants, once thought to be among the most stable objects in the universe, we now know their existence is far from eternal. They too are fading away, incredibly slowly, almost unnoticeably. This single revision in their lifespan estimate is already enough to reshape our entire picture of the universe's final chapter, the degenerate era. In the past, this era was imagined as the longest stretch of cosmic history, a farewell age of extinguished stars and lonely fragments of planets, a slow, lingering goodbye. But now it seems this phase may last much shorter than we once believed. So short it feels unsettling. Even more fascinating, the team didn't stop at calculating stellar fates. They pushed their vision even further, into thought experiments bordering on philosophy. They weren't satisfied with just stars. They also estimated lifespans for much smaller, more familiar objects, things closer to our human experience, and the results were shocking. They went further still, pointing out that neutron stars, so dense they're compressed nearly to atomic size, along with stellar mass black holes, born from collapsed stars, will also decay away within about 10 to the 67th power years. This finding underscores again that even the most stubborn, mind-bending cosmic structures are not beyond change. they too will slowly exit the stage. But that's still not the end of the story. The team's imagination and boldness pushed them even further. They began to ask a daring question. If Hawking radiation is truly a universal law, could it also apply to the ordinary, everyday objects we know so well? Take the moon, for example, or even ourselves, humans. For the sake of comparison, scientists once imagined, almost whimsically, how long it would take for ordinary objects like the moon or a human body, in an idealized situation, through Hawking radiation, to completely evaporate away. The result? A staggering 10 to the 90th power years. Yes, that's right, even us fragile creatures of flesh and blood, tiny and insignificant on the grand scale of the cosmos, still occupy a place on this ultimate timeline of the universe. Of course, it must be said clearly, these numbers are purely theoretical, derived only in a perfectly isolated, idealized setting. In the real universe, objects like the moon or humans would be destroyed by other processes long before, like stellar explosions, orbital decay, or even more basic thermodynamic breakdown. In fact, whether it's Earth's moon, or humankind itself as Earth's representative life form, in the vast flow of cosmic time, we would vanish long before Hawking radiation ever mattered, wiped out by other cosmic mechanisms. We'll be consumed by stellar evolution, the swelling of the sun, or even the breakdown of galaxies themselves, all of which happened far earlier. Even so, the true value of these calculations isn't in predicting the universe's actual timeline, but in revealing the profound power of Hawking's radiation theory and the perspective it offers. It shows us something profound. This mechanism doesn't just apply to extreme cosmic objects, but potentially to anything with mass and a gravitational field, from the largest galactic cores to the tiniest living organisms. This research delivers an unavoidable message. No matter how cold the cosmos becomes, no matter how stable matter seems, even the burnt-out remnants of stars that sleep silently at the edge of the universe cannot escape the fate of ultimate decay. Even if they no longer burn, no longer move, time will still, at the quantum level, erode them bit by bit until nothing remains. The footsteps of time are silent, yet merciless. In a future long enough, not only will galaxies fall apart, but even the most basic building blocks of matter, electrons, neutrons, and maybe even quarks, will slowly vanish through quantum radiation. The universe won't explode. It won't collapse. Instead, it will fade away in a silent, enduring, and absolute erasure into nothingness. This means the so-called final stage of the universe, a cold, dark era of frozen matter, dead stars, and faint radiation may not last for countless trillions of years, as once thought. Newer models shorten this time window drastically, making it more of a brief final note, rather than a nearly endless post-universe age beyond imagination. This discovery naturally points us toward a deep and frankly chilling conclusion: a universe where all energy is diluted, all structure broken down, a final state where entropy has reached its absolute maximum and no usable energy remains to drive motion, life, or even the transfer of information. A universe frozen in silence, where no further change is possible. This entropy-dominated final moment was once believed to take countless cosmic lifetimes to arrive. But now, it seems, it may come much sooner than expected. And that forces us to rethink everything. Does the universe really have enough time to simply grow old? Or could it actually be racing faster than ever, quietly heading toward its final stop? Of course, all this is still unfolding in a future far beyond our reach. A time scale that stretches far past the lifespan of human civilization. But that doesn't mean it has nothing to do with us. The idea of an ending has shifted from an abstract thought into something grounded in physics. It's no longer so distant it can't be imagined. It's become concrete, something measurable, something that can be written into the cosmic timeline. The meaning of this discovery goes far beyond the numbers. It's not just a fine-tuning of the universe's calendar. It's a direct challenge to the very idea of eternity. It forces us to face a truth: the universe's future in an endless horizon. No, it's a destination that can be measured and predicted. Even more importantly, this research opens a brand new window on one of the deepest, most stubborn problems in physics: uniting quantum mechanics with general relativity. It offers an entirely new breakthrough, showing how quantum scale mechanisms can shape the behavior of massive cosmic objects like a key, slowly unlocking the clasp between the two greatest theories of the natural world. This divide has haunted science for decades. General relativity excels at describing grand-scale phenomena like black holes and cosmic expansion. Quantum mechanics, on the other hand, pinpoints the behavior and uncertainty of tiny particles. And yet, these two theories are like different languages. Each describes reality, but they share no common grammar. That's exactly where this research sends shockwaves through the scientific world, because it isn't just a recalculation of cosmic timescales. It digs right into the deepest contradiction modern physics has ever faced: how quantum mechanics and gravity can coexist. And that's the dream. the holy grail that generations of scientists have pursued, but never fully achieved. By extending Hawking radiation beyond just black holes to neutron stars and white dwarfs, objects governed by both quantum effects and intense gravity. This research team opened a whole new window into the crossroads between quantum mechanics and relativity. They didn't just build a bridge in theory. They created a framework that can actually be tested and explored, something almost unheard of in the past. Their theory reconstructs reality with a radical idea. Those quantum effects we thought only happened around the event horizons of black holes, like the creation and annihilation of virtual particles, could actually occur anywhere strong gravitational fields exist. This mechanism isn't limited to the most extreme black holes. It could be widespread, woven throughout the very structure of the universe. This discovery also indirectly supports a hypothesis gaining ground among physicists that space-time itself may not be continuous, smooth, or seamless, but instead made up of discrete quantum units. In other words, time and space, just like matter, may be built from the tiniest quantum particles with the smallest scale, a smallest unit. This is nothing less than a step toward the holy grail of physics, a theory of quantum gravity. And while we may still be far from completing this great unification, this time, we're no longer stuck in abstract math or philosophical speculation. Instead, we're grounding it in real physics and measurable effects. Help connect to major pillars of physics with solid guidance. Over the past few decades, physicists have proposed many frameworks trying to bridge the gap between quantum mechanics and general relativity. Among the more famous ones is loop quantum gravity, which pictures space-time as a network woven from tiny discrete loops, and string theory, which suggests that all fundamental particles aren't points at all, but vibrating strings in higher dimensions, and their vibrations determine each particle's nature. Both theories try to paint a picture of a deeper, more complete universe. But while elegant in form and rich in math, they've always lacked direct experimental proof. It's like we're standing on one side of a giant bridge. We can glimpse the far shore, but never quite touch it. The key building blocks are still out of reach, and Hawking radiation and general relativity might just be one of those long-lost missing stones. Now, by elevating Hawking radiation into a universal principle that permeates the cosmos and applies across different gravitational settings, as a universal mechanism. Researchers at Radboud University may have created a testing ground for these grand theories. It could allow string theory and loop quantum gravity alike to finally be tested and maybe open a path toward a unified language for the physics of the future. At the same time, this research reshapes how we see the cosmos. It doesn't just adjust the timeline of the universe's ultimate fate. It forces us to redraw our blueprint of the far future. Instead of a slow fade, dragging on endlessly, we may be headed toward a universe that shatters and collapses much more quickly. A new cosmic storyline, strangely familiar, yet new. In traditional cosmology, the universe's life is divided into 5 great eras. Each era marks a shift in what drives the universe's evolution. The radiation era, the first tens of thousands of years after the Big Bang, when energy, in the form of light and particles, swept the cosmos. Matter hadn't yet formed, and photons ruled the show. Then came the matter era. As the universe cooled, matter began to clump together. Stars and galaxies were born, and gravity took over as the main architect. This is the era we live in today. Next, the degenerate era, the twilight age of stars. As stars go dark, leaving only white dwarfs, neutron stars, and remnants behind, the universe grows quiet. Then the black hole era, when black holes dominate, slowly consuming what matter remains, until they fade away through Hawking radiation. And finally, the dark energy era, the age of ultimate extinction, when cosmic expansion rules everything. Black holes vanish, and the universe is left with only thin energy and infinite emptiness. These are the 5 great acts of the cosmos, from blazing heat to absolute silence, each stage pushing the universe forward toward its inevitable end. For a long time, scientists believed that between the degenerate era and the black hole era, the universe would endure a long, drawn-out decline, lasting up to 10 to the power of 100 years. A span so vast it dwarfs imagination. Far longer than today's universe age of 13.8 billion years, by an unfathomable margin. But now, new research acts like a cosmic chisel of time, carving down that near-eternal night into something shorter and denser. Take white dwarfs, for example. These stellar corpses were once thought to they could drift alone in the silent cosmos for 1 trillion years. But new models predict they'll completely vanish around 1078 years. Give or take, that's when they'll be gone. And that changes everything about how long we thought the degenerate era would last. What was once believed to be a long, silent chapter in the universe now looks more like a brief transitional phase. Even more striking is the way this new theory redefines the black hole era. For so long, we believed this stage would be the final structured chapter in the history of the cosmos, the last bastion of mass. Black holes were seen as symbols of the end of time, the lonely guardians of the universe's final light. But if stellar mass black holes only live for about years, then the solitude we once imagined and the dark age they would rule over gets dramatically shorter. Not only do black holes bow out earlier, but more importantly, they're no longer the last keepers of the cosmos. That grand chapter once compared to the universe's twilight now looks instead like a fleeting glance, gone in an instant. It's no longer a silent, endless wait. It's more like a swiftly closing finale. Even the grandest structures we thought eternal turn out to be just brief ripples in the flood of time. In the end, these revised theories trigger a chain reaction, like gears tightening one after another, compressing the timeline of the universe's ending. From degenerate stars to black holes, and finally, the great expansion of dark energy. Everything happens more compactly, more decisively. The curtain call of the cosmos is quietly speeding up. So, maybe the universe won't fade into eternity in an endless, drawn-out disappearance. Instead, at specific and predictable points in time, it will rush into absolute silence. Even the tiniest particles that make up everything will eventually run out, dissolving, evaporating, until only the last traces of heat drift across an ever-expanding space-time, fading into the void. And this isn't just a curious game for scientists, nor just a fantasy about the distant future. It forces us to reconsider. In this vast cosmic theater, what role are we really playing? Behind these numbers lie profound questions about reality, about the meaning of time, about the very value of existence. This research is quietly reshaping our view of the cosmos. It reminds us the universe isn't a frozen backdrop. It's a profound machine, powered by the tension between gravity and quantum mechanics. From the collapse of stars to the fading of particles, every second, the universe is inching closer to its own limits. And here we are, living right in the middle of this grand process. More importantly, it reminds us the essence of science isn't to hand us eternal answers, but to constantly challenge, revise, and rebuild our understanding of the world. That power to self-renew. That's the most fascinating thing about science. It never stops. It always searches for a closer truth in the flow of change. Of course, as individual humans, we'll never live to see these far-off cosmic timelines. In fact, most scientists agree our civilization will most likely disappear in just a few billion years, long before the universe itself fades away, which means our brief existence carries an even deeper meaning, because it makes every moment all the more precious. It gives our time here true significance. According to scientific projections, in about 1 billion years, the sun will begin to grow hotter and more intense. Earth's oceans will start to evaporate. Its climate will fall out of balance, and life will slowly come to an end. And in about 8 billion years, the sun will swell into a red giant, finally consuming Earth, a world already scorched and lifeless. A planet long unable to sustain life. By then, our home will be gone forever, and the traces of humanity may survive only as digital records, buried deep within the cold dust of distant worlds. And yet, it is precisely these explorations that give our existence dignity. Every time we gaze at the stars, every time we push forward a new theory, we are, in essence, reaching out toward the very edge of reality. We're not just measuring the size of space. We're chasing the question of what reality truly is, the ultimate question of existence. Thank you for joining us on this journey across billions of years, through the destinies of stars, and to the very boundaries of the quantum world. Along the way, what we've encountered is not just numbers, formulas, and particles, but the deepest silence and the most profound echoes of the universe itself. If this journey has left you awestruck, confused, or even a little unsettled, don't worry. You are not alone. Every single one of us, when confronted with such vastness, feels our own smallness. But it is exactly because of that we yearn to understand and to transcend. So keep your curiosity alive. Keep looking up at the stars, while staying grounded in the world beneath your feet. Because in this fading universe, it is our thoughts, our questions, and our imagination that give it meaning. Even if, one day, everything disappears, miracles will always remain.